If you have ever tried to turn the steering wheel with the engine off, you already know it feels like a heavy gym workout. That intense resistance is your first real clue. You are not suddenly weak, and your car is not broken. It is simply not helping you anymore. Today, we are going to see exactly how the steering system quietly multiplies your physical effort, and why guiding a 2-ton machine feels completely effortless as soon as the assist wakes up. It is easy to think that you are twisting the entire vehicle when you steer, but what you are really doing is fighting against 4 small patches of tire rubber stuck to dry pavement. At a complete standstill, those patches grip the road incredibly hard. The steering wheel has to physically scrub the tires sideways just to start a turn. That takes real rotational torque at the rim of the wheel. Without any help, that effort can easily reach 25 to 40 newton meters. But with power assist, the exact same move drops down to just 2 to 5 newton meters. Your hands simply aim. The hidden system brings the muscle. Purely manual steering could technically do the job. Engineers used to gear it down heavily, meaning you had to twist the wheel more and more just to move the tires slightly. That made the steering agonizingly slow. It was acceptable on the open highway where you barely move your hands, but it was miserable in a tight parking spot. The hardest part is always low-speed maneuvering. The tires scrub and the suspension geometry pushes back. You need extreme precision and massive physical force at the exact same time. Power steering solves both of these problems. It senses exactly how hard you are trying to turn and adds just enough push directly at the steering gear. The secret to making this feel natural is an incredibly clever sensor built around a thin bar of steel called a torsion-bar. It hides deep inside the steering column, right between the input and output shafts. When you pull on the wheel, you physically twist this steel bar a few degrees. We are talking about 2 to 7 degrees of rotation. That tiny elastic twist is clean and smooth, offering a direct mechanical measure of exactly how hard you are pushing. Traditional hydraulic systems use that physical twist to move a fluid valve. Modern electric systems read that exact same twist with magnetic or optical sensors. It is the brilliant truth teller in both designs. In a hydraulic assist system, you essentially have a small oil power plant running up front. A belt driven by the engine spins a dedicated pump, building fluid pressure anywhere from 1,000 to 1,500 pounds per square inch. When you turn the wheel, that little torsion bar nudges a rotary spool valve. The valve acts as a gatekeeper, routing high-pressure fluid to one side of a hydraulic piston that lives inside the steering rack. This compact, palm-sized piston violently shoves the steering mechanism with several thousand newtons of force. The rack slides and the wheels turn. A pressure relief valve naturally caps the peak pressure, so the components live a long life and the feel remains stable. Electric power steering takes that exact same concept, but completely swaps out the fluid hoses for a smart electric motor. The torsion bar still twists, and digital sensors measure the exact angle of that twist. A computer control unit instantly calculates the need and spins a compact motor mounted directly on the steering column or down on the rack. Through internal gears or a small belt, this motor adds rotational torque exactly where it counts. On many mid-sized cars, a rack-mounted motor can instantly add 40 to 100 newton meters of assistance. Heavy vehicles can push well above 150. During a hard parking move, it might briefly draw a few hundred watts. Once you stop turning, the electrical draw drops down near zero. Electric steering took over the automotive market for a few very simple reasons. A hydraulic pump is driven by the engine belt, which means it runs anytime the engine is turning. Even when you are driving straight down an endless highway, that pump eats power and generates waste heat. Electric assist only sips electrical power when you are actively moving the steering wheel. That single change saves a measurable amount of fuel for many cars, often adding a couple tenths of a mile per gallon and dropping carbon emissions. It also completely eliminated the drive belt, the messy fluid, and most of the driveway leaks. Because the steering is controlled by software, engineers can add advanced features like lane keeping and automatic park assist using the exact same hardware. But excellent steering feel is not just about raw power. It is about perfect balance. When crawling at parking lot speeds, you want maximum assistance, so the wheel glides smoothly in your hands. But at highway speeds, you want the wheel to stay firm and calm. Most modern systems intentionally ramp the assistance down as your speed rises. Additionally, natural alignment elements like caster make the front wheels want to straighten out on their own as the car rolls forward. The power assist is carefully mapped to blend perfectly with that physical self-centering force. Modern electric systems can even artificially add gentle texture and damping to filter out a shaking tire or a sudden crosswind. When tuned correctly, it feels entirely natural. To understand what that effort at the rim actually means in the real world, you just have to look at the geometry. A typical steering wheel might measure about 36 centimeters across. If you were forced to feel 40 newton meters of torque without any power assistance, it would be the equivalent of physically pushing the rim with 140 to 220 newtons of force. Picture locking your arm and leaning your entire upper body weight into the steering wheel just to turn it. With power assist active, you are suddenly back to a light, one-handed push. That drastic contrast is exactly why the dead engine steering test feels so shocking. You are finally experiencing the raw job with no helper. Exactly where this electric muscle lives also changes how the car feels. Column assist systems add the torque high up under the dashboard. It is a lightweight and space-saving design, but the internal gears see the entire heavy load, which can introduce some mechanical flex. Rack assist systems add the torque all the way down at the steering rack itself. By operating directly on the mechanism that moves the wheels, it can deliver significantly larger numbers with far less flex in the steering path. Because of this, many mid-size and larger cars rely entirely on rack assist to deliver a tighter feel. Smaller city cars often stick with column assist to save weight and space. Let us look at the true hidden cost of hydraulic power for a moment. A belt-driven pump operates constantly. At a standard idle, it can draw a few tenths of a kilowatt of engine power. At higher engine speeds on the highway, it can easily eat 1 to 2 full kilowatts. That stolen engine power has nowhere to go, so it simply turns into waste heat in the hydraulic fluid and a small external cooler. You pay that continuous energy penalty even when you hold the wheel perfectly dead straight. Electric assist completely avoids that hidden tax because the electric motor sits perfectly still when you sit perfectly still. Unlocking the steering rack with software introduced entirely new tricks. Because a computer is in charge, the exact same electric motor that helps you parallel park can gently nudge the steering wheel during highway lane keeping. It can autonomously park the entire car at low speed by operating safely within its pre-programmed torque limits. It can instantly add a touch of damping when a heavy crosswind hits the side of the car. It can even soften the violent kickback through the wheel when you strike a deep pothole. All of this is accomplished with absolutely no extra pumps, hoses, or valves. It is entirely achieved through clever code and careful safety limits, so the system never runs away. With computers physically turning the steering wheel, you might wonder how engineers keep it safe. The secret is relentless monitoring. The computer system watches that tiny torsion bar twist like a hawk. If the twist angle increases rapidly, the system instantly provides help. If the twist goes to 0 because you let go of the wheel, the help immediately falls away. Engineers program strict physical and thermal limits into the code. There are also fully redundant backup paths, ensuring you can still manually steer the vehicle if the power assist goes completely dark. The ultimate aim is incredibly simple. Help you flawlessly when you ask, and never surprise you when you do not. Caster is the quiet mechanical hero of natural self-centering. If you tilt the vehicle's steering axis backward just a bit, the tire contact patch naturally trails behind the pivot point. As the car rolls forward, the physical drag forces the wheels to align themselves with the path of travel. That is exactly why the steering wheel returns to the center all on its own after you make a turn. Alignment settings like toe and camber also dictate how heavily the tire resists changing direction. The computerized assist maps are carefully written to respect and blend with these natural physical forces. This guarantees the steering wheel always feels deeply connected and steady rather than dangerously floaty. Even the tiny torsion bar has a fascinating story regarding how we perceive feel. If you could somehow watch the bar while you were actively steering the car, you would see only a few microscopic degrees of twist. In a transparent laboratory bench demonstration, You can clearly see that the computer control unit constantly tries to cancel out that twist by immediately adding motor torque. The primary goal is to keep the bar as close to its relaxed center state as possible, while the heavy rack does all the actual moving. You never actually notice this microscopic deflection taking place because the electronic reinforcements arrive almost instantaneously. A short look back at history puts all this engineering into beautiful context. In the 1920s and 30s, an engineer named Francis W. Davis developed the earliest automotive power steering concepts. The technology made its first major public splash in 1951 when the heavy Chrysler Imperial debuted a system called Hydraguide. The colorful advertisements proudly bragged that the mechanism did 4/5 of the physical steering work for you. Decades later, in the late 1980s, fully electric power steering made its production debut on tiny Japanese city cars. One famous early example was the 1988 Suzuki Servo. By the early 2000s, electric assist became the absolute default technology across almost every vehicle market. Real-world moments often make the raw numbers feel incredibly real. Picture a heavy off-road truck, fitted with large, deflated tires. If the engine stalls while the truck is wedged on a rock, the steering wheel feels like it is cemented in place. You restart the engine, the hydraulic pump finally wakes up, and suddenly the wheel glides smoothly against immense tire friction. Conversely, if you're driving on a sheet of glare ice, you barely need any assistance at all. The tires simply slip before any significant forces can build up. But on hot, dry pavement, you need absolutely all the help you can get. The vintage Citroën SM even featured an exotic hydraulic setup that actively pushed the steering wheel back to center at highway speeds. It felt incredibly strange at first, but utterly brilliant once you trusted it. So what exactly happens if this invisible assistant suddenly fails? The crucial mechanical link always stays intact. The solid metal gears still firmly connect your hands to the front tires. If you are crawling at parking lot speeds, the required effort immediately spikes back to that brutal manual load. But once the vehicle is actually rolling down the road, the job gets significantly easier because forward momentum and rolling tires naturally reduce the scrubbing friction. A famous example was the 2014 recall involving millions of General Motors vehicles equipped with electric assist. Drivers experienced a sudden jump in parking effort when the assist intermittently shut down. The cars were still completely steerable by design. The real danger was simply the sheer element of surprise. There are two primary mechanical ways to translate the rotation of your steering wheel into the left and right motion of the tires. The vast majority of modern passenger cars use a rack and pinion design, which is precise and compact. Many older classic cars and heavy trucks relied on a recirculating ball steering box. Those older boxes were almost always paired with high-pressure hydraulic fluid assistance. Regardless of the mechanism, the steering ratio dictates the personality of the car. A standard ratio around 16:1 feels calm and predictable for everyday driving. A quick steering rack, measuring closer to 12:1, feels wonderfully sporty and responsive in corners, but requires far steadier hands on the open highway. The PowerAssist computer maps are precisely tuned around these physical gear ratios so that parking remains completely effortless. To truly appreciate the steering system, here's a final scale check that completely reframes the entire process. Deep inside a hydraulic rack, there is a tiny piston measuring perhaps 25 to 30 millimeters across. When fed with 1,200 pounds per square inch of fluid pressure, that little disc can violently shove the steering tie rods with several kilonewtons of raw force. That is an astonishing amount of power, radiating from a metal component roughly the size of your palm. Ultimately, your hands on the steering wheel are just casting a vote for where you want the vehicle to go. The power assist mechanism is the actual muscle executing your command. If the front tires were physically bolted to the ground, that tiny piston would generate enough force to drag the entire nose of the car sideways. Once you truly notice it, you will feel your invisible teammate working with you on every single turn. If you enjoy getting a clear look inside the everyday systems we take for granted, consider subscribing for more. We build videos explaining the inner workings of complex engines, silicon computer chips, massive suspension bridges, undersea internet cables, commercial planes, and the sprawling power grid. If this breakdown helped you understand your car a little better, leaving a quick like helps the channel find more curious people just like you. See if you can spot your hidden helper the next time you pull into a parking space. You are never actually muscling 2 tons of metal and glass around a corner. You are simply negotiating a friction deal with 4 fist-sized patches of rubber pressed heavily into the road. Power steering is the brilliant piece of engineering that steps in, and wins that exhausting argument for you every single day. If you appreciate clean engineering stories like this one, hit subscribe and check out the other videos on the channel. Thank you for riding along, and we will see you next time.